Do you want to? Yeah. Okay. Do you want to check your? Do you have slides?
Yes. Do that. So
yeah.
Let's see. I have to 화면. Okay. But this is it. So, okay, so let me see. Can you see it?
Yes.
Yeah. I can see it. Yeah.
Okay.
Yeah. Yeah. Okay. That's good. So that works. I forgot, Yong-Geun, I wanted to introduce you to some of the people. Do you know everybody here?
Not really. Yeah.
Okay, sorry. I should introduce you. Have you met Anton or you? No.
I might have come across Anton somewhere, but I don't think we meet in person.
Where is
Right?
Anton? Are you still there, Anton?
Yeah, I'm waving my hand.
Oh, okay. Right. And then Nikita, you met. Yeah, I think maybe you. Yeah. Okay. I see Lisa there. Hi, Lisa. Jeffrey, you probably know. Yeah.
Let me see.
Yeah, we have. Anyway, but they may be off. Eckhart is on. I see Eckhart Rankin. Dima, the people who have their video on. Francis.
Let's see. How can I see the gallery?
How do you see the gallery? Nikita, how do you see the gallery?
Well, this should be, you know.
Yeah, I have to
like
maybe up and down probably.
Yeah, I mean, in the usually in the top right corner of your screen, there should be an option.
Yeah.
But perhaps we're ready to begin.
Yeah. Okay. So so let me. So Yong-Geun, I'll be sharing your talk. So today, we are extremely happy to have Yong-Geun Oh speaking on. Yong-Geun and I were students together way back in Berkeley. Right. So he will be speaking on Lagrangian fibers of the Gelfand-Cetlin systems. Yeah, please, Yong-Geun.
Okay, so thank you very much for the invitations. These days I have been kind of isolated in Korea, so it's very good to see many people face at least. Okay, so today, what I'm going to talk about today is some joint work with the two young mathematicians, Yoosik Kim and Yunhyung Cho. Okay, so this is the outline of my talk. So I first go over this well-known Gelfand-Cetlin systems, and then I talk about some diagram phase correspondence and to identify what the Lagrangian fibers, how we can detect the Lagrangian fibers of the Gelfand-Cetlin systems. And then, I'll talk about, and then which of those fibers are non-displaceable. That means which you cannot find any Hamiltonian isotopy which displace that particular fiber from away from itself. And then finally, I talk about the machinery of detecting that non-displaceability using the Lagrangian flow theories. So this actually whole thing requires quite sophisticated deformation theory of Lagrangian flow homology. So Okay, so I guess the first part, most of you maybe know better than I do, but I'll just quickly go over what the main this integral systems is. So everybody knows what partial flag manifold, I suppose. So the partial flag manifold is a complex manifold parameterized by this nested sequence of complex vector subspaces in Cn. So these are standard notations. And then if the flags are complete, oops. Oh yeah, then it's called complete flag manifold. It's a homogeneous space, as written there. Okay, and there is a canonical, actually symplectic form on this partial flag manifold as cosine orbit. So these are descriptions. So all these partial flag manifold are symplectic manifolds as a cosine orbit. And these orbits are classified by these eigenvalues, this nested sequence of eigenvalues. And the symplectic form is this celebrated form by Kirillov Kostant Souriau, written as here. And it turns out they are completely integrable systems in the sense that if this flag manifold has dimension 2n, and you can find this n independent function in involutions that satisfies these conditions, and each function is smooth. And actually, that's I should do okay. So they are smooth on open dense subset, and these differentials are linearly independent. And actually, the associated completely integrable system to this Gelfand-Cetlin systems, those functions are not smooth everywhere. There is a certain part where they are just continuous, but not differentiable. And they lies in the boundary of this so-called Gelfand-Cetlin polytope. So this is the famous theorem by Guillemin and Sternberg. And those, so let lambda jk be the j's largest eigenvalue of the upper left k by k sized submatrix of that Hermitian matrix characterizing that cosine orbit. And then those eigenvalues forms are actually completely integral system. In other words, considering those as a function on this cosine orbit, they are in involution. So if you look at this particular matrix and associated cosine orbit, that's symplectomorphic to F3, the complete partial flag manifold F3, corresponding to the eigenvalues 2, 0, minus 2. And more interesting example is the following. These particular examples, F3, will appear frequently in my talk because this provides one very simple but interesting examples to see some continuum of non-displaceable Lagrangian tori in it. And one interesting fact about this particular example is that there is some boundary point of the polytope whose fiber turns out to be Lagrangian, which is diffeomorphic to S3. and that appears as the limit, Hausdorff limit of some continuum family of Lagrangian tori from the inside of polytope. So I'll talk more about this in detail later. Okay, so now the fibers of this Gelfand-Cetlin system for in the interior all tori, but yeah, so but there are certain Lagrangian fiber that is located in the boundary face of this polytope. So we want to know which facet or face of this polytope carries some Lagrangian fiber. And that can be studied by looking at the so-called ladder diagram of this system. So a ladder diagram is the set of boxes, each of which contains one component of those eigenvalues I mentioned before. Those are arranged in this anti-diagonal manner. I mean, depending on people use different diagram, but we are using this particular shape of this diagram. And the red point is called origin, and the blue point is called top. We will call top vertex. And then the important notion is the positive path. The positive path is the shortest path from the origin to one of these top vertex. And by definition, a positive path can go either upward or to the right-hand side. And this is a theorem by An and Cho and Kim. There is an order-preserving one-to-one correspondence between the graphs drawn by collections of positive paths satisfying those conditions. And then the faces of Gelfand-Cetlin polytope. So each graph corresponds to one face of this polytope. So for example, if you look at a collection of positive passes, what is the satisfying? Let me go back. So what is this? Okay, so okay, the person satisfies this condition. Where is this? So the positive path is shortest something. I guess this star means just to go up or down. So if you look at this path for each top vertex, there exists at least one positive path from the origin to the vertex. So those are the positive paths and not other ones, like this one is not.
Sorry, just a question.
Yeah.
So faces, these are faces of all codimensions?
Yeah. Yeah, the codimension is the number of, so there is a correspondence. So let me continue here. So if Fi be the corresponding face to a subgraph of these positive passes, so you look at this order preserving, and so let me. So let's see something. Okay, so here so this condition star is written here. So if for each top vertex, there exists at least one positive path from the origin to the vertex. And we say that's the condition star, sorry. So for example, if you look at this first one, and there is one positive path from red to this blue one. So to each one of these ones, so this is the corresponds to the face of this polytope. And then this, you look at the second one. The second one also has that property. So the one positive path to each. And then the wait a minute, something. So this one.
No, but it's fine. Let's
This is
continue.
Sorry, may I ask why is the last one not good? Because it looks like the one on the right. Because it looks like so you have what one.
Which one are you talking about?
And it seems like there is a path from the red point, from the red vertex to each of the blue ones, right? So you go like from the red one, you go like one to the right and then two up, right? So you get to the blue vertex two, and then if you just go straight to the right, two to the right and one up, then you get to -2.
So if you look at this union of this passes, so the first two examples, you see that there is at least one shortest path from the red to right, I mean red to blue dot. But the next two one, you look at this the bold path, segments, the line segments, and then there is no shortest path from the red to this blue one, and the same there is similarly the fourth example violates that one. So that's the correspondence. So each graph drawn by the collection of positive paths, if those that satisfy the conditions, then it corresponds to faces of Gelfand-Cetlin polytope. So these are more examples. So we are looking at that particular examples I was talking about, and this is the polytope corresponding to this complete flag manifold F3. So this diagram shows all the faces, and maybe edges too. So the number of these boxes, closed boxes, says the dimension of the face. So the first one has 1 dimension, the last one is 0 dimension, and then the third one has 2 dimensions. The green corresponds to that one. So that's the way how it goes.
So sorry, just a naive question. No, you can also think of those faces as in these scintillation inequalities, right? Some of the inequalities are actually equalities. What is the relation between the two descriptions?
Oh, you mean, so the relation, for example, let's see. These are the ones. So gamma 1, 2, gamma 1, 1, gamma 2, 2. These are coordinates of this R3. Okay. So each phase is determined by those inequalities. So I think this one corresponds to, I think my order. So let me see. My ordering is the X, I think X, Y, Z. So let's see. So maybe you should look at this as the maybe origin. And then this phase is the X1. So it's it's like the inequalities determined by this momentum polytope. So you should think of some equations. I think let me see what are the precise. Coordinate. Okay, so the coordinate is
no worries. We can probably figure it out. Like,
yeah. So okay. So in this coordinate is lambda. Okay, lambda 2, 2. Lambda 2, 2 is x coordinate, and lambda 1, 2 is y coordinate, and lambda 1, 1 is z coordinate. Okay, and then these the phase, the inequalities is given by those. So maybe I think the next page will have this one. Oh no, I don't have it. So let me, okay, yeah, I should do. Yeah, you can actually, those are the coordinates. So what I'm saying is the coordinate is lambda 2, 2 is x coordinate, and lambda 1, 2 is y coordinate, and lambda 1, 1 is z coordinate. So out of this, you can actually figure out which phases corresponds to which. Okay. So, I mean, this standard definitions. So submanifold Y is called isotropic, and a submanifold is Lagrangian if its dimension is exactly half of this. So now I want to make some comparison between the Gelfand-Cetlin system and toric moment map. So let me first go over the toric case. We know all the interior fiber is Lagrangian torus. And if the point is not in the interior, those are the actually isotropic. Cannot be Lagrangian because its dimension is smaller than n. Okay. However, in the Gelfand-Cetlin polytope case, this Gelfand-Cetlin polytope is actually can be regarded as a moment map of some toric degeneration of this Gelfand-Cetlin system. So because of that, some of this the boundary phase could have the Lagrangian fiber, which doesn't happen in the toric case. So that's the big difference between the Gelfand-Cetlin system and toric system. And another difference is that in terms of this particular integrable fiber, there's almost the toric fibrations. The Gelfand-Cetlin fibration is only continuous on this along the boundaries. But in the toric case, they are smooth everywhere. So let's talk about which phase is a Lagrangian of this Gelfand-Cetlin system. And that can be actually, there is a nice criterion for that. So let me explain this. So there is a nice combinatorial criterion for the Lagrangian phases. So to explain this, let me introduce this notion of L blocks. That's just the blocks look like that. So a ladder diagram is said to be L block fillable if L blocks cover the ladder diagram, obeying the following properties. The interiors of two L blocks must not intersect. The interior of L block does not contain any piece of any positive path in that graph, given graph. And then the blue edges in this L blocks. The blue edge means the top these edges and the rightmost edges. Okay. Should be mapped into the pieces of this positive path. It's kind of tight. It cannot move. So if you that particular given graph has this fillable properties, and that corresponding phase must be Lagrangian. So let's look at some examples. So let's look at this F7. And F7 has this eigenvalue, the nested sequence of eigenvalues. So let's look at these two particular phases and see which one satisfies that L block criterion. Okay. And the first phase is 7-dimensional because there are exactly 7 the square boxes in it. And then the next one has 11-dimensional phases, and the dimension. Let's check. Okay, so let's put this L block this red L block to this one. And of course, this L block is too big, so we cannot put this L block into here, so it doesn't count. But if you look at this blue block, L block, and you could see in the first one, you can actually put this L block exactly tight for positions. And similarly, you can do that in the second one too. Let's try this smaller one. So you have to try every L block to fit into that way. And then here, for the first one, this is the all possible tight filling. And actually there is yes. And then for the second one, that's this. Okay, the first, so, and then this is one block, so you can fill in. And then there is, okay, on the right-hand side, you see this one block. If you put that white squares there, then that particular filling does not satisfy the tight conditions for the second phase. So that shows the first phase is Lagrangian, but the second phase is not Lagrangian. And in fact, the dimensional does not match for the second one. So, but at least this shows that this L block criterion really can tell the Lagrangian phases. Okay, so now let me go to the next section about non-displaceability of Lagrangian submanifolds. this is standard definition, but just to set the conventions. So my Hamiltonian vector field is defined in this way, not with the negative. And Lagrangian manifold is said to be non-displaceable if you cannot find any Hamiltonian diffeomorphisms that moves L from itself away. So for example, if you look at this Lagrangian manifold on sphere, only the area bisecting curve is non-displaceable, because on sphere, the area preserving diffeomorphism is the same as Hamiltonian diffeomorphisms. So all these small circles is displaceable. And actually, maybe why do we consider why do you concern this non-displaceable Lagrangian manifold? And you know the Allen has this famous creed about everything is a Lagrangian manifold in symplectic geometries. And in fact, actually those good collection of non-displaceable Lagrangian manifold should be regarded as the core of the ambient symplectic manifold. And that statement can be said in the language of so-called Fukaya categories. And those good collection of non-displaceable Lagrangian manifolds form some kind of generator of this so-called Fukaya categories. So that means it basically contains all the, most of the essential intersection theoretic information about this ambient symplectic manifolds. Okay, so in relation to Gelfand-Cetlin fibers, as I mentioned, I want to understand which Lagrangian fibers are actually non-displaceable. And there is one very universal criterion given by Anton without, the final product does not use anything about Floer theories. So, but, okay. So, but there its construction uses it. But anyway, so their theorem is there exists at least one non-displaceable Gelfand-Cetlin fiber on the system. This is a corollary of a very general theorem of theirs. Their general theorem is you look at any collection of finite collection of functions in involution. You regard this as a kind of integrable system or partially integrable system. And then the Anton-Polterovich's theorem is there is at least one simultaneous values whose pre-images is non-displaceable. So in particular, any toric fibration or Gelfand-Cetlin fibration or maybe almost toric fibration carries at least one such fiber. And then more systematic study of this question was first carried out by Nishino, Nohara, Ueda. So they've showed that there exists at least one non-displaceable Lagrangian Gelfand-Cetlin torus fiber on a Gelfand-Cetlin system. So Anton-Polterovich's theorem does not say which fiber is actually non-displaceable. For example, a priori, that fiber could come from the boundary. Then fiber may not be torus. But Nishino, Nohara, Ueda's theorem is there is at least one non-displaceable fiber from the interior. So it's that torus. And yeah, Nohara and Ueda showed another theorems. There is one non-displaceable Lagrangian Gelfand-Cetlin fiber whose topology is U2 in this glass manifold. Okay, so now I'm particularly interested in these particular examples. Why is that so? And you look at this red line in this polytope, and I will show you that all the fibers from based at this red line are actually non-displaceable. They are all tori, but its limit, the fiber at the particular vertex is also Lagrangian, whose topology is actually S3. Okay? And then, by some continuity argument, if you show that all the fibers from the red lines are non-displaceable, then that Lagrangian sphere located at the vertex is also non-displaceable by continuity argument. So that's how we will show you. And an interesting thing about this particular example is that we have this completely answers to the question about which fibers are displaceable and which fibers are non-displaceable. And in fact, Paviniak showed that by some probe method, the probes method, all other fibers are indeed actually displaceable, except those fibers coming from this red line. Okay? And then we showed that all those the fibers coming from this red line are non-displaceable. So combining these two theorems, this completely answers to that particular question about non-displaceability for this example of F3. So let's look at some more examples of this one. And you can see that these three phases, P2, P3, P4, actually satisfies that A block criterion. You can check. So that all of these phases are actually Lagrangian. And then that particular example I showed you, F3, that has some continuum family of Lagrangian tori coming from the interior fiber. It turns out this is not an accident phenomenon. In fact, this is a universal phenomenon for this particular complete flag manifold. You look at any complete flag manifold Fn, and then there is that similar this continuum family. Okay. Okay. So now this is the end of the first part of talk, which is about the combinatorial criterion of Lagrangian phases, and then the main theorem about this existence of continuum family of non-displaceable fibers. So in the second part of the talk is how do we prove this? And to explain this, I needed to go over a little bit of this so-called Phloemology theories. And Phloemology theory for compact Lagrangian submanifold, in general compact symplectic manifold, involves this particular ring of so-called Novikov rings. I wrote down some universal Novikov ring. The universal Novikov ring is nothing but this formal power series of one formal variable capital T, and that has this real power. The exponent is real power. So you're looking at the sequence of real numbers. That sequence is proper in the sense that it either stops at finite stage or otherwise it has to diverge. Okay? And that provides some kind of a topology on this a ring given by filter valuation. So you can, for any formal power series, you define the valuation of this particular formal power series as the exponent of first primary component. The lambda 1 in that expression will be the valuation of the formal power series. So that provides some topology on this ring. And in that topologies, this formal power series converges. Okay? So this field has, as a ring, has one maximal ideal, that is lambda plus. Okay. I already know there's lambda plus and lambda 0. So lambda plus means there is no the constant terms. And lambda 0 means this associated ring. Okay. Lambda is the associated field of lambda 0, this ring. The quotient of lambda 0 by lambda plus is just the base coefficient ring. That could be either C or rational numbers or any other field, algebraic closed field. Okay. So now let's talk about Lagrangian flow theories. So flow first introduced this infinite dimensional mode theories, and then define some kind of flow homologies. And to simplify the whole discussion, I just look at the pair that is one compact Lagrangian submanifold L with its Hamiltonian deformation phi L. Okay? So you look at this pair of this Lagrangian submanifold in the assuming transversalities, you will have a finite number of intersections. And this intersection provides some kind of a generator of this modules. You look at the module generated by this intersection number regarding those intersections as the basis. Okay? And then the boundary, there is a boundary map. The boundary map has this matrix element that is given by the number of holomorphic disks and this cornered disk, which I denote by beta here. Okay, so you look at this and try to find or map this phi from this strip to the target symplectic manifold. One of the boundary goes to one Lagrangian submanifold L, and the other boundary goes to another Lagrangian submanifold phi L. Okay, and assuming some finite energy condition, or in this case, you assume that particular oval shape has finite this map phi has finite symplectic area. And you count those holomorphic curves. Okay? And that number of holomorphic curves will be the matrix coefficients from Q to P. Q and regard Q and P as basis element. So delta P is a linear combination of those intersections, and the coefficients are precisely that number of these holomorphic curves between Q and P. If this particular map has boundary property, in other words, if delta square is 0, then you can define the flow, these homologies. That's what these days called flow homology. And this boundary condition is satisfied, for example, if L, the pi2, relative pi2 of L is 0. I mean, that, okay. The one important fact of a holomorphic map is that it always has a positive symplectic area. And on the other hand, the symplectic area is also homological, topological invariant. So if pi2 vanishes, relative pi2 vanishes, any holomorphic disk with a boundary lying on L must have a zero symplectic area. So that's why in that case, delta square is always 0. However, this relative pi2 condition is not satisfied, and delta square may not be 0 in general. The obstruction for this delta to be satisfied, this delta square equals 0, arises from the existence of the holomorphic disk. Okay. So holomorphic, so I'll say more about later. If there exists a holomorphic disk bounding the given Lagrangian manifold, those holomorphic disks provides some obstruction. And in general, the delta square turns out to be the so-called the potential functions, which is a general function of so-called one-point open Gromov within invariant. So this open Gromov within invariant is your 1 point, means you look at all holomorphic disks with one marked point on the boundary. And you ask the number, you try to count those holomorphic disks with that 1 point constraint. Okay, and there could be many, and the area may be all different. So there could be many different holomorphic disks with different areas. So you collect all those data as a general function using that formal parameter capital T with the exponent, the area of that holomorphic disk. That's what this general function. I wrote P for the potential function, which I will call. And so what we have to do, if this delta square doesn't vanish, we cannot define this flow homology. In other words, we cannot define any symplectic invariant that is invariant under Hamiltonian isotope. The one important general fact is that if this flow homology is defined, this flow homology is always invariant under the Hamiltonian isotope. It doesn't change. So in particular, if the flow homology doesn't vanish, that means you cannot find any Hamiltonian diffeomorphism which displaces L from itself. So to show this displaceability, we really need this flow homology. So when this disk is not 0, then what we want to do is we want to deform this whole theory by certain deformation parameters. And there are two kinds of deformation parameters. One deformation parameter comes from boundary. So in other words, you look at we are looking at the Lagrangian submanifold inside symplectic manifold. So all those so I told you that this holomorphic disk bounding this Lagrangian submanifold is obstruction. So we want to kill those boundary cycles arising from this holomorphic disk by choosing some cycle or chain of boundaries. So I sort of pictured here the way how we deform this boundary map is by inserting those chains from the boundary Lagrangian, meaning that we are going to count the holomorphic map that intersect with those given cycles. Okay, that cycle may come from this either interior from the boundary or from the interior. So the left-hand picture here is a boundary insertion. What I'm going to do is these blue and red dots are the cycles, boundary cycles, that where these holomorphic disks intersect the given boundary cycles. The right-hand side picture, that cycle could come from this ambient symplectic manifold. Okay, so this picture basically restricts the holomorphic disk. You only count holomorphic disk that intersect with the given cycles. And this deforms the original definition of this flow map, because we are now using the counting the holomorphic disk with some constraint. So those obstructions I mentioned already come from this holomorphic disk. So let me explain how this works slightly. Okay, so this picture is that this the sphere, this half sphere is a holomorphic disk, and the boundary now lies in this Lagrangian submanifold. And there are boundary marked point and the interior marked point. Okay, so this MK plus 1 XLJ beta is basically modular space of holomorphic disk with K plus 1 boundary marked points. And beta is relative homotopy class of the disk. And you consider this evaluation map as a correspondence. So there are K plus 1 marked points. One of the marked points should be regarded output point, and all the others are input. So I'm pull back some differential forms from L, K's power of L, and to that correspondence, and then push forward by EV0. So that's the way how this MK map is defined. So MK beta is just the pullback push forward of differential forms via this correspondence. Okay? So for each homotopy class beta, we are given this K-linear map. Now you collect them over all this homotopy class and multiply this formal power t to the omega beta. That provides this MK map. So MK is a formal power series operator written in this way. So the exponent of formal power parameter is just symplectic area of disk. And it turns out this collection MK satisfies so-called A-infinity relation. Okay, so I just wrote down, and this whole thing called A-infinity algebra. And in general, this is so-called, it starts from M0, and this is the reason it's called curved A-infinity algebra. M0 is the usually called the curvature of this infinite algebra. So the official is that each Lagrangian submanifold carries a natural this infinite algebra, and that is this infinite algebra is the kind of algebraic structure that explains how we are going to deform the original flow map. Okay. That particular bounding these cycles I mentioned before satisfies that infinite Maurer-Cardan equation. And this Maurer-Cardan equation is nothing but the M0 after deformation. Okay. So for each solution for this Maurer-Cardan equation, you have a deformation of this Phloemology so that you can define the associated Phloemology. So you should just regard that each solution of this infinite Maurer-Cardan equation will give you some Hamilton invariant that is unchanged under the Hamiltonian isotopy. And I denote this solution set, the set of all gauge equivalence classes of these solutions, ML, the frac ML. This Maurer-Cardan modular space. And actually, I was talking about so if the Lagrangian submanifold, I mean this Maurer-Cardan equation may not have any solution. So if that happened, I don't care. So just ignore, discard them. If it has some solution modulo this potential function, this identity, and it's called Wicklian obstructive. So I just we are going to talk about Wicklian obstructive Lagrangian submanifold. The official is all the Lagrangian fibers and Gelfand-Cetlin fibers are Wicklian obstructive. So we can define these potential functions for those Lagrangian submanifolds. So I already mentioned how the boundary deformed the flow cohomology. So for each solution of this Maurer-Cardan equations, we can deform the flow homologies to define boundary deformed flow cohomologies. And you can do the same game for the ambient cycles. And so now you again choose some ambient cycle B, and that actually deforms the whole infinite structures. Previously, I just wrote the German M without the superscript B, but now I have a superscript B. That's the ambient cycles. So each ambient cycle deformed this whole infinite structure of this symplectic manifold. Okay, and that provides deformed Maurer-Cardan equation I wrote here. And so the point is that we can deform this flow cohomology in two different ways. One is boundary using boundary cycles, and this one is using the bulk cycles. So this is famous boundary bulk kind of map or correspondence in physics. So, okay, and the theorem is that if you, the point I already mentioned, if the flow homology is, whatever deformed flow homology is well defined, that, and if that flow homology is non-trivial, then that is non-displaceable. So how would we detect the non-triviality of these homologies? And it turns out that, of course, it looks very complicated, but at the end of the day, the non-triviality of this flow cohomology can be detected by using some critical point theories. So these potential functions that appears as in solving the Maurer-Cartan equations actually provides the very nice criterion for non-triviality of this flow cohomology, thereby non-displaceability of Lagrangian manifold. So in other words, there is some symplectic topological phenomena is completely determined and can be seen by some critical point theory of some non-Archimedean analytic functions. So this is exactly some one manifestation of this famous homological mirror symmetry between the symplectic manifold, geometry of symplectic manifold and the geometry of a complex manifold. So the potential function can be well defined for all Turing manifolds and Gelfand-Cetlin systems. So in fact, in the tori case, this potential function can be easily read off from the momentum polytope itself. Okay, so each facet of momentum polytope provides one essential holomorphic disk. So in this monomial, what it says, that each codimension one face of a momentum polytope, there is one monomial associated to it. And this monomial is the data is completely determined by momentum polytope. So here, VF is the normal vector of that phase facet, and LFU is the usual defining function of momentum polytope. So it turns out this defining function of momentum polytope is exactly the symplectic area of associated holomorphic disk. So let me, I think I have the, oh yeah, here is example. So if you look at this CP2, we know the CP2 has a momentum polytope, just this equilateral triangles. And there are three phases, and each phase, the normal vector is 1, 0, 0, 1, and -1, -1. And you see here, monomial is exactly corresponding. The power is U1. U1 corresponds to 1, 0 normal vector. So 1, 0 normal vector is this Y phase. The second monomial corresponds to the X phase because its normal vector to X coordinate axis is 1, 0, 1. And then this last one, we know this this third edges equation is 1 minus U1 minus U2. Okay, the momentum polytope is corresponds to the positive inequalities. So that's the way how the potential function can be read off. This can be read off for any compact Turing manifold. So for example, in this case, the potential function, those three holomorphic disks, I think I have, no, I don't have the picture. So holomorphic disk is exactly the, actually the normal line stopping at this given the point in the momentum polytope. Okay, and in this case, all those three holomorphic disks has the same area. So this has the same power. The 1/3 is the barycenter of this momentum polytope. You see that those exponents are the same. So in fact, in this case, this potential function is just simply y1 plus y2 plus 1 over y1 and y2. You can easily compute that critical, the point is 1/3, 1/3. And that is, this particular toric fiber, therefore, is non-displaceable because it's a critical point. That particular potential function has a critical point. And this is first proved by Cho in his thesis. This is the beginning of this whole story in tori case. So he proved this theorem in all CPN. And then
sorry, just I'm a little bit confused about those critical points. Isn't it like 1-1? I don't know, like I'm just naively computing the partial derivatives, right?
Oh, sorry. So it's a 1/3, 1/3 is the location of the space point, the fiber. Okay, and
yeah.
So if you compute the differential, what is it? ddy?
Yeah.
No.
Yeah. So I think it's 1-1, not 1/3, 1/3. But I of course maybe I'm doing.
Wait.
Yeah.
No.
Sorry. On another note, I don't know. That's probably for Lou to manage, but we should probably negotiate the timing, right?
No, I think, yeah, okay. So 1/3, 1/3. If you take the derivative y1, you see 1 plus 1/y1 squared, y2, right? And then you solve 0 and you differentiate in y2, and then you will see that 1/3, 1/3 is a critical point. I mean, 1/3, 1/3 carries a critical. The point is that 1/3. No. It's not a critical point. That's what I'm saying is that it's 1/3, 1/3. Yeah, I think this one's critical. It has a critical point.
And I think this critical point is 1-1.
Is that right? So
I don't know. That's at least that's
one
that's
minus
what my calculus is saying, but I don't know. Of course, that doesn't matter so much, right? But
okay, the point. What I'm trying, let's talk about this. The point is that this one has a critical point.
yes.
So if you look at the U1, U2 other point, and then you did not have a critical point in this. So then you can do the same game. So here is the Gelfand-Cetlin polytope, and similarly you can write down this potential function in a similar way, and you can compute those. In this Gelfand-Cetlin case, the detection of this fiber that carries a critical point is much more complicated. And sometimes you cannot find a critical point unless you further deform using the bulk parameters. And that's what happened. And this requires some study of what kind of ambient cycles you are going to choose. And this involves the particular Schubert cycles as the bulk deformation parameters. So, and the bulk deformed, using bulk deformation of Floer theories. And this involves some solving some non-Archimedean critical point equation for these polynomials. And sorry, using this, particular examples, we can prove those all red lines are non-displaceable. The upshot is that to detect this, we really need to deform this whole thing using bulk parameters arising from some particular Schubert cycles. So sorry I'll stop here.
Well, thank you, Yong-Geun. Thanks a lot for the talk. Are there any questions? Are there any questions?
I have some questions.
Yeah.
Okay.
Yeah.
So I haven't quite understood. So you're proving that on this red line, on some analogs of that red line in higher dimensions, you have non-displaceable fibers, right?
Yeah, yeah.
But how is it, do you know, or is it conjectured that all the other fibers are displaceable, or there might be other non-displaceable ones, or like how far is it from for dimension 3? You said it was a full classification. How far is it from full classification in the general case?
I don't know about the current status of that question, but I don't think it's known in general. So this F3 is maybe the only, as far as I know, that maybe, there could be Paviniak may know better. But
and why is that? Is it because for outside the red line, it's difficult to control this potential function, or I mean, what's the reason why we don't know in other places? Probably, I guess it's my ignorance. I probably haven't got all the.
Are you talking about this positive case or negative case? To see the certain fiber is displaceable, you really have to construct the Hamiltonian isotope.
Oh, I see.
Right?
I see.
And it turns out that there is a method of constructing this Hamiltonian isotopy using so-called probe method. That's what Macduff sort of applied in tori case. And some of that method can be generalized to this Gelfand-Cetlin system too. That's what Paviniak applied.
I see. You're saying that to prove that something is displaceable is just a different game, right? So,
right.
And maybe
to see the non-displaceability, you really have to use this analytic, the Floer theory machinery.
And maybe one more point about which I got a bit confused. So how is it, you were saying at some point monotone, this means a particular choice of lambdas, right? Does it,
yes.
So what's this choice, and does it work only in that monotone case, or it doesn't matter?
Oh, by the way, actually in my talk, I didn't, I think I theorem, in the theorem, I think in the beginning, I mentioned probably I'm looking at the monotone case, monotone this.
So monotone is what lambdas at the top lambdas are equidistant, right? Or what is monotone?
Monotone means, you mean the general definition, or in this?
No. But in this particular case for those flags, so that means that, right? Something, at least all your lambdas, they looked equidistant, right? So is it?
Yeah, exactly. Yeah, they are kind of the monotonist has something to do with this equidistance or
and it all works only in the monotone case, or it can work outside the monotone case.
I mean, the general theory works does not require the monotone case. In theories, you can actually define, I mean, but for actual computation of these flow homologies you defined, you need some way of understanding this modular space of holomorphic disks. So the monotone case is kind of a starting point for the study of this holomorphic disk. Of course, starting from there, you can move around and you can change the coefficients, because the existent holomorphic disk is kind of a rigid phenomenon. So even if you change the symplectic form, this holomorphic disk will not disappear until it hits some particular wall. These walls are kind of can be read by studying how this area of holomorphic disk changes. So once you understand the monotone case, you can actually also apply this to the non-monotone case, except those walls. So you really have to understand this wall crossing, the particular where this wall appears in this discussion.
Thank you.
Yeah.
Oh, you're welcome. Yeah.
Okay, maybe any other questions or quick questions? Okay, maybe if not, it's kind of getting late. Maybe we just thank Yong-Geun again.
Okay, thank you very much.
Thank you, Yong-Geun. Thank you. Yeah. Let's see, we can